Okay, we are noon time now. So, any questions so far? Any questions so far?
No, sir.
Okay. This session is set up for question and answer. So, if no question, I'll briefly go over what this week we will do, and then that's it. Okay. So this week, basically, we are on the lecture 5 and 6. That is on the Danevit-Hartenberg table and metric. And then next one, also the lecture 6. So lecture 5 and 6. Lecture 6 is actually on the inverse kinematic. Okay, inverse kinematic. So this week on these two topics. So first one is like last week we covered the homogeneous transform matrix. Okay, so this week the Danevit-Hartenberg table is a continuation of the homogeneous transformation matrix. Two are related. Okay, so Danevit-Hartenberg table is used to systematically generate the parameters that can be used in the homogeneous transform matrix. Okay, so basically this chapter is like that. So Danevit-Hartenberg's number, they are very complicated. If you look at the textbook, it's very complicated, but basically they are 4 parameters. A, D, alpha, and R, 4 different parameters. Okay. So if we look at this textbook's equations, they are very, very complicated. Okay. And these different parameters' purpose is to generate the metric for the homogeneous transform metric. Okay. So let's look at the easier set. The B7, okay, from here. This is the Danevit-Hartenberg in simplified version. Okay. So if there is a robot serial manipulator, so serial manipulator is the most common industrial robot, and they are designed as a series of link connected with motor H80 the joint. So there are different kind of joint. There's one kind of joint called rotator joint. Okay, and there's one kind of joint called prismatic joint. So prismatic joint, you only have the displacement. Okay, rotational joint, you have both. You have the rotation. Okay, so that's the okay, and then this is one of the model for the robot serial manipulator of the 6 degree of freedom. Okay. So one terminology, N effector. N effector actually talking about the finger. So usually a robot arm, we talk about arm, hand, and the finger. So arm, hand, and finger. Okay. So robot arms' main purpose is to actually position your hand. Okay, so your hand may be, so you may have a XYZ coordinate. You use your robot arm to control the hand at certain XYZ location, and then at the local, okay, at the local robot operation, we usually call it robot wrist. So you do rotation, finger open, finger close. Those are operation on finger of robot wrist. Okay. So first thing is like workspace. What is workspace? Okay, workspace is the region or the geometrical model that your robot can reach. Let's assume that you have only one rotator, one-dimensional rotator, and your arm's length is fixed. and you are doing rotation. So you basically rotate like this. So this circle actually is your workspace. Okay, this circle is your workspace. Let's assume that this robot is a little bit more complicated. So right here, there's a rotator. Here it has a second rotator. Here it has a big arm over here. Okay. So now let's assume that actually everything is straight. The top is right here. Okay. And then this one can rotate, but the lowest point you can rotate move to is right here. Okay, it's right here. And then you circle for 130 degrees. So in the middle you can reach here and here. Okay. So you can rotate 360 degrees. So basically the workspace for this one would be a sphere. It's actually moving around and actually making the whole ball. That is where your end effector can reach. So basically, this the geometrical model that your end effector can reach, we call it the workspace. Okay, we call it the workspace. So that is the workspace. I just talking about the basic idea. Okay, so singularity. What is singularity? Singularity means that if I have 2 degrees of freedom, okay, let's assume that right now I'm actually a robot arm with rotator here. Here I have second rotator right here. Okay, so end effector right here. So if I actually fix this rotator, so it actually like a baseball bat. Okay, this one actually fixed. The rotator joint in the middle actually fixed. So I can move like a whole circle, but that's one line. That's one circle. That's a one-dimensional workspace. If this joint move, it can be like this. So you can touch almost everywhere inside this circle. Okay. So we say that the singularity happens if you fix the joint here. This is the theta 2 never change. Here, theta 1 and theta 2. If your theta 2 never change, then we talk about it actually one singularity. Okay, it's only one dimensional. It dropped your workspace to one dimensional. And when it dropped to one dimensional, some location you may not be able to reach. We call it singularity. Okay. And the singularity. So here is another example for singularity. There are certain locations, this robot arm, because your prior operation, so certain location that you cannot reach. Okay, cannot reach. But you can readjust, get out of the singularity. Then you will be able to reach some point that you originally cannot move to. Okay, that's called removal or bypass the singularity. Okay, so this talking about the singularity and the workspace. Okay, next one, Danevit-Hartenberg table. So Danevit-Hartenberg is based on the homogeneous transform metric. So homogeneous transform metric, you want to have a 3-dimensional rotational metric here, 3 by 3, and then 3 by 1 displacement vector. Okay, you put into one homogeneous transform metric. But when we model the robot, we want to actually have a systematical way of doing it. So this talk This Danevit-Hartenberg talk is how to systematically set up this transform metric. So there are 4 rules you must remember. These are very important rule. Okay, 1, assign frame to according to the Danevit-Hartenberg rules. Create a Danevit-Hartenberg rule parametric table, and then plug in those table value to homogeneous transform metric, and then multiply the metric together to form the total modeling for the robot. Okay, so Danevit-Hartenberg frame number 1, you must use the right hand rule. Okay, right hand rule. Right hand rule. What is the right hand rule? If you study the if you study the math, there is something called cross product. Cross product means A vector, B vector, A vector cross product with B cross product vector will be equal to C's vector. This value would be the absolute value of the A vector times B vector's absolute value times sine theta. Theta is the angle between A vector and B vector. So this roughly is equal to the area right here. Okay, formed by this is the length of A. Length of A here. This one is the length of B here. Length of B here. Okay, and then C vector is in this direction. Okay, so magnitude wise, C's length is equal to A's length times B's length times sine theta. Direction wise, it actually is over this angle. So how can you determine this angle? This one is called right hand rule. Okay, so what is right hand rule? Right hand rule is like let's see. Let me start sharing. Right hand rule is, let me choose my, okay. Right hand rule is like I have a hand, right? This is right hand, my right hand. My right hand, so if A vector is this direction, that is the where the finger's direction. B vector is the palm direction, it's actually right here, okay? So your direction is like this. Some people use this. This one is your A vector, this is B vector. So A vector cross product to B vector, this one up would be your C vector's direction. Okay, one more time. If you use a right hand, 3 finger, this one's A vector, this one's B vector right here. C vector is on top, it's the right hand, okay? And then if you use one hand, this one is actually cross product up, okay? That's the direction. So we use the right hand rule to determine where the cross product vector should be, okay? That's the right hand rule. So some of the coordinate may not follow it, may not be acceptable. Okay, you have to see if this one cross over and then this direction is A, B, C. This is okay. Okay, this is okay. This one is not. Okay, this one is not. Okay, be careful. That's the right hand rule. So there are 4 rules for Danevit-Hartenberg's frame rule. Number 1, the z-axis must be the axis of the revolute or the direction of the motion. Okay, so you need to know about z direction. So what is z direction? Z direction means you have x, y, z. Okay. if you set up a coordinate system, like assume here you have a rotator. Okay, here you have a rotator. So this one, if your x is right here, y is right here. Okay, then you rotate along the post. You have a theta. So SY cross product, your Z direction is right here. Okay, that's the rotator's axis is called Z direction. If your joint is prismatic, that's as soon as H extender, and then you extend this direction. So this should be G. SY should be somewhere here. I'm sorry, X should be this one, Y should be this one, because you need to cross product using right hand rule. Okay. Okay, so that's what right hand rule should be. So let's assume this one. This one is a 3-joint 4-frame. So right here I have a frame, a base frame. Okay. Second frame is based on this rotator extender, and okay. So there's a theta one that you rotate in this frame. There's a Z direction here. You have X and Y here. So this is the second rotator. You have a theta 2 here. Third one, you have an extender that has a D displacement over here. And then finally, your observation frame on the end effector. So 4 frame means that you have the 4 frame means that you have the original frame, SYD right here. You may have an original frame doing SYD here. Second frame, this is a rotator, SYD here. Third one, on the extender, you have D over here. Fourth one is the observation frame of the end effector. So frame 0, frame 1, frame 2, frame 3. Okay. 3 join 4 frame, 3 degree of freedom. 3 degree of freedom because you have 3 variables. The theta 1, theta 2, and D, 3 variables. Now determine where your end effector should be. Okay. So rule number 1 is determine everyone's Z direction. So Z direction should be your rotator's center axis or the extender's direction. Rule number 2. Rule number 2, the x-axis must be perpendicular to the Z frame before, and also it must follow the right-hand rule. So x must be perpendicular to the Z. Okay, so we assign some x to there. So the y direction must be following the right-hand rule. So we set up this. So now the 4 frame for the Danevit-Hartenberg frame was set up. Okay, let's pick this one as an example. This one is actually the one we are talking about here. Okay, this is real world example. So Danevit-Hartenberg matrix, you do have what? You set up 4 frame. You will have three row. Okay, 4 frame you will have 3 row. Row number 1 is frame 0 to frame 1 transition. Row 2 is actually frame 2 to frame 3 transition. Row 3 is frame 3 to frame 4 transition. Okay. So on each one, you have You have the X revolve angle and the G revolve angle. Okay. And then you have the frame X movement and the frame G. So on each frame, you would have 3 frames would have 2 rows, 4 frames, 3 rows. Okay. And there are theta alpha. Theta alpha are both angles. R and D are actually the movements. Okay. So what is theta? What is alpha? What is this D? Okay. That's earlier. Okay. That's in the note. In the other note right here. Let's look at this. Okay. This one Danevit-Hartenberg in this one, in this lecture 5 note here, it do have a definition for what is D, what is theta, what is alpha and R, alpha and R. So let's look at theta. Theta is easy. Okay. Theta means how much angle you rotate. So it's the angle on the previous G direction. Okay. So let's assume that we have a base right here. Our original frame is X, Y, Z. Okay. So right here, we have a frame 1 on the rotary here. So on this frame 1 over here, your Z is this direction. Your X is this direction. Y is actually this direction. Okay. So basically, in frame number 1, we do have a 1 parameter theta. Theta is right here. Okay, I'm sorry. The Y direction on frame 0 should be in this direction. So theta is an angle that you move along the axis from here to here. Your base change how many angle that actually is theta. Okay. So that's the rotational theta that you would have. Okay. Now let's look at what is alpha. Alpha is also an angle, but alpha is different. Alpha means that my rotator is actually right here. I'm rotating along the axis, right? But I rotate. That's actually here. I would have a rotator theta. Okay, but my arm may have an angle with my rotator. That actual angle is called alpha. So alpha rotate about the new axis X and put G in the desired orientation. So basically, some rotator do have an actual alpha angle. Okay, actual alpha angle. This is different from just like you have rotator, you should be rotating here. That is a theta, but somehow your joint right here may have a certain angle with your original rotator. That actually is called alpha angle. Okay. If there is a certain angle, actual angle. Okay. So when you rotate, you're assuming you should be rotating. It should be rotating in this circles rotate the angle. Okay, right here. But in fact, it is not, because your joint location may have a certain angle, maybe even perpendicular to your joint angle. Okay, so that's called alpha. So what is D? D is that how much displacement you have. So your rotation is on the base, but you may have a distance from the base to the real next angle. Okay. to the top. So the base frame, if your base frame is right here, but your next one, the rotator may have a certain height, okay, and that certain height from that the base to the height of that rotator will have a distance of d, okay. So that's d, and we also have another one called r. So r is the distance along the x-axis alternative, the radius rotating about. So that's actual distance of the d. Okay, these are just some concept. Let's go back to the example right here. Okay, so we need to set up this table. So let's look at the robot arm one more time. After you set up the frame, you do consider this rotator original base. You have x0, y0, z0. Okay, and there's a A1. This A1 is the length from your base to the top right here. That's A1. Okay, theta 1 is how much it rotates. Okay, theta 1 is how much it rotates. So theta 2 is the second angle that it rotates over here. And then there's a A2 from this point to the center of this point. That's called A2. That's the distance when we fill in the table in the Danevit-Hartenberg table, okay? So theta 1 should be a theta that you rotate on the first frame. The other one is D, okay? The D area displacement is the A that you show up here, okay? So we do every single one of these, okay? So let's see. First is theta, okay? First is theta. First is theta, the angle that rotates along x n minus 1. N minus 1 is this one. Along, along G minus 1. Rotation of the n minus 1 toward the n minus 1 toward the n. Sn is this direction. So when one's x to when zeros, okay. So when 0 is not changing, when 1 means that the x, if my theta rotate, then my robot arm will go to here, okay. And then the whole rotator is right here. So my x1 is right here, okay. So there's an angle that you go to, that's called theta, okay. So it will be 0 plus theta 1, okay. So basically your xn's movement primarily caused by the theta 1, okay. So along the way, we also calculate theta 2. Theta 2 here, S1 is right here. S2 and S1 and S2 actually overlap because we can actually put them together. Okay, we put them together. So let's go back to here. When we do modeling, we actually have S1 and S2 separate. But since S2 and S1, this distance is fixed, so we can move this frame to here, and then put extra extender and distance A in the middle. So we can move the X2 frame to be overlapping with S1 frame. But they have orientation difference. So we move over the X2 and S1. So now your x2's direction due to the rotation of theta 2. Okay. So that one, you got 90 degree plus theta 2. Okay. It's starting from 90 degree. Your S1 and S2 already had 90 degree, and your theta 2 move again. Now again 90 degree plus theta 2. That's the angle you get. Okay. Third one, you actually have a friend number 2 and number 3. X direction you have from here, X direction of the X2 to X3 along the Z direction. It actually is 90 degree here. Fixed. It is fixed 90 degree. So you can determine the theta 3 to be 90 degree. Any questions so far?
No, it's okay. Yeah.
So these four rules are the detailed way to determine your theta, alpha, R, and D. Okay. So we do one by one. Okay. According to the rule of specification, you should be able to get it. Once you get them, you use the number to calculate. You plug in systematically. You will come out with the Danevit-Hartenberg of the transform matrix from N to N1. N to N1 means that two friends, from friend 1 to friend with respect to friend 0. That means how much change your cost by friend 1, by friend 0's rotation, and when you observe on friend 1. That's called Hn with respect to. So it's friend 1 with respect to friend 0, or friend 2 with respect to friend 1. And the N number is the angle we see here on the table. And you plug in, you'll get this Danevit-Hartenberg metric for that one rotational metric. Okay, and then after you get every table H0, 1, 1, 0, 2, 1, 2, 3, 2, you get different table, and then you multiply together using a big metric operation. Then that's the program we have. You can download the program to look at it. Okay, so basically that's the program. That's the Danevit-Hartenberg program. Any questions so far?
It's okay. I got it.
We basically go over the idea. Okay, we don't go into the detailed mathematical model. Just tell you what you can study. Okay. So that is the first topic of the Danevit-Hartenberg metric. So you look at the lecture 7 in the undergraduate material. Right here, this textbook is extremely hard to understand. Okay, a lot of math. But if you are interested, you are okay to read it. Okay. So here, let's assume that we have a 3 rotator. Okay. So 3 angle. Okay, 3 angles. So theta 1, theta 2, theta 3. And then you can come up with a 3-link planar arm. Planar means that you are 3 joint, but actually, no matter how you swipe your arm, it will be on one surface, right? Because you have a rotator in the middle. Your arm, you rotate again. How much can you do? It's just actually rotating in a 2-dimensional space. It cannot go up, down. There's no up, down. It's only XY change. Okay? There's 2 degrees of freedom. So anyway, you come up with some number using calculation. Okay? And here you talk about all kind of the arms model. Okay? Using the Danevit-Hartenberg. Okay? So there are all kind of model you can have, and you keep doing every single one. Okay, that's the modeling. Okay, Danevit-Hartenberg is a algorithm that help you to do calculation. Okay. So next one, let's look at the inverse kinematic. Inverse kinematic is the reverse of the Danevit-Hartenberg matrix. So Danevit-Hartenberg matrix or homogeneous transfer matrix is that you based on how much rotation you have. Okay, your theta 1, theta 2, theta 3, and d displacement to determine where your n effectors xyz location should be. Okay, this is called forward kinematic. Backward kinematic is that, okay, I told you I will go from this point 1 to point 2. I don't care how you did it. Then you need to calculate the amount of the theta 1, theta 2, theta 3 for me. And that I just give you the n effectors location. You need to calculate for me. That's called inverse kinematic. Is that okay so far? So forward kinematic means that using the control of theta 1, theta 2, and the d, okay, and the displacement numbers to figure out where the n effector is. That's called forward kinematic. Backward kinematic or inverse kinematic means that you know where my arm n effector should be, and then you backward to calculate how much theta angle or d I need to have. Is that okay? This is forward kinematic is from you join variable to get the n effector's position. Inverse kinematic is from the n effector's orientation and position to find out those joint variables. Any questions so far?
No,
Okay, so now let's assume we do have a modeling for this. Okay. So you want to you can come up with whatever metric you have. You want to do inverse kinematics. So you solve the metric. Then you take you for half a year to finish it. So that's actually very time consuming. Okay. Solving the inverse metric. So actually sometimes we don't encourage to do that in that way. Okay. So we use a trigonometry or some other method to figure out those inverse kinematic. So let's use an example also from the undergraduate notes. One more time because it's easier. Okay. Let's look at the inverse kinematic. There are many ways you can solve it. Okay. It's mostly using the trigonometric methods. So we do have this one, okay, set up the metric like this, okay. So let's assume that we want to solve a nonlinear equation. So we know that xy where it is, right? And you go backward to find out what theta 1, theta 2 is. This is assuming you have robot arm with two rotators, theta 1 and theta 2. Okay? But that is not easy. You get the xy, you try to solve theta 1 and theta 2. That's not easy. Even though you can formulate it using the Danevit-Hartenberg metric. So there are several different workaround methods. Number one is the graphic method. So that is we have cylindrical manipulator, 2 degrees of freedom, that is, put the parameter on. Okay. Then next one, we do know about the SY, and then you have a rotator theta that you rotate, and the extender D over there. That's actually a simple example of this, but we don't care about the height. We just look at the SY location from here to here. You see where you should be, okay, and with extender and the angle theta. So in that situation, we know about XY, final XY location, okay? We do know about A to D, A to A3, but D is available, theta is also available, okay? So based on the SY we have, we can determine the total length from here to here should be A2 plus A3 plus D, displacement D, okay? So, and we have the equation S1, S equals R plus D. So this one and this one is R plus D. So R plus D times cosine theta should be the X right here. Should be this is the amount of X. So R plus D times sine theta, that is the amount of Y over here. Okay. And then your angle Y divided by X is your tangent theta. Right? Let's call it T. So we know that it's HT. So basically your sine theta should be T over T 1 plus T squared, X square root, because it's a triangle. Okay. Okay. Y over X is T. So by doing that, you have a T, you have Y over R plus D. You should be able to calculate this, the theta using the tangent table. Okay. And then after you sub the theta, you can also sub the D. Any questions so far? This is based on a rotation result, and then use a trigonometry to sub the variables. Okay. Okay, let's assume that we have another robot that actually is extender plus rotator. Again, this one also in 2-dimensional angle. Okay. So we know about X and G. We want Y. Okay. Even X, G, and Y. We try to find D and theta. Okay. So we can set the location. We know about the location of this guy is X and Y and G. Okay. So this is XG. This dimension is by XG. Y is the vertical one. Y fixed. Y is fixed. Okay. Because this time Y direction is right here. So YH is fixed. Given these informations, then we can calculate using the XA3 and R. We can sub the R number. Okay, total length. And then you can sub the D. Okay. Using it. Okay, next one we have the manipulator, 2 rotator. Okay. So 2 rotators combine angle and combine length. You use them to sub it. You should be able to figure out what is phi 1, phi 2, phi 3. And then you can sub the theta 1 and theta 2. How much angle the theta 1 should be and how much angle the theta 2 should be. Okay. Okay, so that's what we have today for the Danevit-Hartenberg metric and also inverse kinematic. Okay. Any questions so far?
It's okay.
Okay. If no question, that's it for today. Okay. This session is set up for answering questions. So if you have question, please let me know. Okay. One more call. Is there any questions so far? Homework or whatever question? No? Okay. No, that's it for today. Okay. Thank you for participating. See you next week. Okay. Bye-bye.
Okay, thank you. Bye bye.
Bye-bye.